topic of the rotational motion. So we start our journey in Physics 1 by talking about the linear motion, which is somehow a revision of what you have learned before. So we have the kinematics, we have the Newton's laws, energy, and then linear momentum. That is something you have learned before, I believe. And then we have the what? The rotational motion. Okay, let's come back to. And then we have the rotational motion. Of course, in the rotational motion, many of the things are quite similar to the linear motion. I would only say they are similar, although there are some, well, there are very fundamental difference. In the linear motion, most of the time you consider an object which can be treated as a point particle if you consider all the masses are located at the center of mass. In the rotational motion, most of the time we consider an extended rigid object. And because of the shape, there would be a difference in their rotational inertia. And that is the topic of the moment of inertia. So we have talked about it for quite a long time. The moment of inertia is related to the inertia of an object during the rotational motion about a certain axis. So it depends on how the masses are distributed from the axis of rotation. Objects with masses that are further away from the axis of rotation would have a larger moment of inertia. And in most of the cases, we would have to resort to the integration to calculate the moment of inertia. But luckily, in here, we would be focused on the use of the concept, moment of inertia. So first of all, we have some tables which would tell you the moment of inertia about the center of mass for an axis that goes through the center of mass for typical geometries. And secondly, if you have axes that are parallel to the axis that goes through the center of mass, let me see, I should have it here. Okay, here, this one. If you have rotation about axis that goes through the center of mass, like this one, it has the relation with another rotation about another axis that are parallel to the original axis of rotation. So these two are parallel. And in that case, the moment of inertia about the axis that goes through the center of mass, let's call ICM, is related to the moment of inertia about a new axis, let's call it I, by the parallel axis theorem. Parallel axis theorem can be found in this page. So it would be I equals to ICM plus md squared, where m is the total mass of the object and d is the distance between the two parallel axes. Important word at here is parallel axis. The new axis must be parallel to the original axis that goes through the center of mass. That is very important. So with that, we could calculate the moment of inertia for a lot more different systems. And we have seen it in the tutorial worksheet. And we have also talked about the Newton's law in the rotational form. Basically, the one that we use quite often would be the F equals to ma in the linear form. And here in the rotational form, it is the net torque. The net torque equals to the I times alpha. I is the moment of inertia, alpha is the angular acceleration. So if you have an object that is under the action of net torque, then it would suffer a rotational acceleration or deceleration. And it is related to also the moment of inertia of the object about the axis of rotation. Work done. The definition of the work done is similar to the case of a linear motion. In the case of linear motion, F times ds. In the case of a rotational motion, the net torque, well, actually the torque times the d theta. We mentioned that in many of the calculations, clockwise motion would be given a negative value. So if a torque assists the clockwise motion, it would be given as a negative torque. And if the motion is in the anti-clockwise sense, in the counterclockwise sense, it would be regarded as positive. So if the torque and d theta are in the anti-parallel sense, one goes clockwise, one goes anti-clockwise, you would have negative work done. And that is what we have seen in the quiz on the 5th of October, where you have the torque and the displacement in the anti-clockwise direction. And that is a negative work done. So kinetic energy in the rotational form, 1/2 I omega squared. Once again, quite similar to the linear form. And last Thursday, we talked about the, we also talked about the rolling. And last Thursday, we talked about the angular momentum. Now, many of the students ask me why there exists linear momentum, angular momentum, even if the object is moving in the linear sense. It is like you are asking whether the object would be treated having a linear momentum when it is not moving. Well, okay, it is not moving, so the value of the linear momentum is 0. But you would also argue that it is just m times v equals to 0. The linear momentum in the physical sense, it still exists. And the situation is more complicated in the rotational sense. It depends on where you define the axis of rotation. So the angular momentum actually exists as long as there is a motion of an object. Motion can be in the clockwise sense or in the anti-clockwise sense or even not moving. The angular momentum is just a physical property, and it could be considered no matter it is moving or not moving. And if we are having a object moving in a linear fashion, like the particle at here, moving in a certain direction under the action of a force, well, okay, it has actually a linear momentum as shown in the diagram below. And as long as it is away from the axis of rotation that we consider, then we could say that it has an angular momentum about this axis of rotation. It is defined in this way. So angular momentum can be considered just as a physical parameter, as long as you have a certain axis of rotation and the object is moving about it, not necessarily moving in a circular orbit. That is the idea. So we have gone through a lot of examples in the angular momentum, and in particular, we talk about the conservation of the angular momentum. That means if there is no external torque, net torque is equal to 0, then the angular momentum would be conserved. That is a very important concept, similar to the case of a conservation of linear momentum. One thing I have missed at here is that we have actually discussed the angular momentum in two different formats. The first format is regarding the motion of one particle about an axis of rotation. This is the axis of rotation going through the paper perpendicular to the plane. And the particle is here, moving in a certain direction. So the momentum is in this way. For one particle moving about a certain axis, the angular momentum about that axis is calculated by this equation. L equals to R cross P. Remember, this is a vector operation. It is a vector product. The magnitude is given like this: R times P times sine phi, where phi is the angle between the R vector and the momentum vector. Of course, in this particular example, the two vectors are perpendicular. So the angular momentum is just R times P, or MVR. And this is the case for particle moving about a certain axis, and you could calculate the angular momentum in this way. For an extended object, which you have a collection of particles, you could use the similar trick. You have the angular momentum of individual particles given in this equation, in angular momentum of individual particles, and then you add them together. Of course, at the end, that would become integration. And omega for all the rotating particles, they are the same. So the sum of mr squared becomes the moment of inertia. So that is why we have the angular momentum for a rigid object, for an object with a collection of particles, I omega. That is how we will in this way. And we have talked about various conservation laws as well in the last lesson. So we have basically gone through the rotational motion, and the next two topics, they are somehow not very well connected in the lecture notes, but in any case, they are very significant concepts in the mechanics. So we would cover them. At least for the first small topic that we would see, it would be actually related to what we have learned in the last few weeks. That is the linear motion and the rotational motion. And that is the concept of a static equilibrium. So in this unit, we would be solving some problems that is related to the static equilibrium of rigid bodies. So for a rigid body, of course, we mean an object that has an extended shape. So it may be a rod, it may be a person. Well, okay, a person may not be very rigid, so unless you tie them up. So most of the time, we will be considering, for example, beams, rods that are rigid in shape. And equilibrium, by definition, It means the object, it is moving with either constant velocities or constant angular velocities relative to an observer. Now, I'm not saying that the velocity must be positive or negative. It can always be zero. In particular, in this set of lecture notes, we only consider actually the case where the velocities are equal to zero. This is what we call static equilibrium. Objects not moving. There are objects that are moving and they are still in equilibrium. Some of the common examples involve the movement of, for example, liquids between two places. The flow of liquid from one place to the other, if it is exactly the same as the flow from another place to the first one, then there would be no change. And that would be still in equilibrium, but it is a dynamic situation. Here, the case is that all the objects are not moving, no rotation, no linear motion. And of course, having the objects in static equilibrium doesn't mean that it has to be easy. Although the concept is actually quite straightforward, because if the objects are not moving and if they keep doing so, if the objects are not moving, zero speed, zero angular velocity, and if they are kept doing so, then there is only the following situation. You have no net force and you have no net torque. Because if there is any net force, objects accelerate, but velocity changes. And if there is net torque, then object rotates with acceleration. So if it is in static equilibrium, the conditions here must be satisfied in general. What I mean in general is that we are talking about three-dimensional case. Net torque equals to zero, net force equal to zero. But just for understanding the concept, let us try to make the things a little bit simpler. Let us try to make the things a little bit simpler and analyze the situation in which we have equilibrium considered only in a plane, in the what we call XY plane. So what happens in the XY plane? Just assume it may not be the case in your examination or whatever, but let us assume that the X may be the horizontal direction, is the horizon, and the Y is the height direction. So it is the X and it is the Y. So it could be motion in the X-axis, or it could be the motion in the Y-axis. Motion in the Y-axis. And finally, in the plane, the object might rotate. It may rotate about the origin, or it may rotate about actually any point in your diagram. But in our consideration, we are considering equilibrium. So what it means is there would not be any motion in the X. There is no any motion in the X direction, no any motion in the Y direction, and no rotation at all about any axis that goes along the Z direction. So that is why you will see the three equations here. First one and the second one are quite straightforward to understand because there is no motion in the X and Y direction. the torque about the z-axis has to be 0. And the z-axis, or actually the torque, is actually about any axis that goes perpendicular to the plane, to the xy plane. And the location of the axis is actually arbitrary. In the first instance, it might be quite hard to absorb this point, but let us try to put it in the linear case. An object is not moving from this point upward. The axis, the origin is at here. Even if you move the origin to a new point, okay, I'm messing with things up. Even if you're moving the origin about a new point, becomes here, this object, it is still not moving in the y-axis. So you see what I mean? When you change the axis, the object is still stationary. That is the important message. So you have the rotation about any axis that runs perpendicular to the plane is equal to 0. Okay. Next, of course, we would try to see some examples and see how that could be achieved. At here, we have a seesaw, another toy that has disappeared with time in the playground. And actually the playground has probably have disappeared with time as well. But in any case, you may still find it in the Google. It basically is a piece of board, a wooden board or a metal board hinged at a certain point. So that is something we call a pivot, typically. And here you have two persons sitting on the opposite sides of the seesaw. The mass of various parts are given. And the support, here we call it the fulcrum. It is right under the center of gravity of the wooden board. The father is at a distance d from the fulcrum, and the daughter is at a distance L/2 from the fulcrum. So the length of the whole wooden board is actually L. First, you're asked to determine the magnitude of the upward normal force exerted by the support on the board. Now, if the whole system is in equilibrium, then you could first draw a force diagram of the whole system. The force diagram involves basically the wooden board at here, and it would be under the action of some forces. For example, the weight of the board itself, so that is a large mg. That is the weight of the father, mfg, and then weight of the daughter, mdg. And then finally, you need to support the whole thing. Otherwise, it just fall on to the ground. So that is where the normal force comes from, where the upward reaction force comes from. So that is how you determine the first part of the question for the normal force. And then we do not expect any horizontal force in this case, because all the forces are in the vertical direction only. And then for equilibrium, we also need to have the rotation equals to 0. That means the net torque about any point in the system is equal to 0. Now, the advantage of calculating the equilibrium is that you could decide the torque to be extracted at any point, because our definition of the static equilibrium requires us to have the torque equal to 0 about any axis. So in order not to make fun of yourself, you first try to pick a point where it is easiest to calculate the torque. And here, let us try to first pick a point that is easiest to calculate, and that is right underneath the board, underneath the center of mass of the board, and that is the flocum. So we consider the rotation at the flocum. What are the possible contributions of the torque about the flocum? Why we pick this point is because with that, we could eliminate the contribution from the weight, and we could eliminate the contribution from the normal force. They are right at the flocum. R is equal to 0. No torque due to these two forces. So the any torque is due to the father. It is an anti-clockwise torque. So MFG times D is the positive value. On the other hand, the daughter cause the rotation in the clockwise sense. So it is minus mdg times L over 2. And they are in equilibrium, so it has to be 0. And in this way, you could calculate the relation between the D and various parameters. Suppose in here, we could choose another location to calculate the next torque. And that is actually done in the last part of this slide. So for example, you could find the torque about an axis perpendicular to the page and pass through the father's location. So instead of having the torque right at the flocum, let us try to do the things in a slightly more complicated way. Let us do the things in a more complicated way and calculate the torque about the father. So there are altogether 3 forces. The clockwise torque from the daughter and the weight of the board, they are coming from these 2 terms. And then you have the anti-clockwise torque from the flocum, the normal force from the flocum, and that is the anti-clockwise torque, so positive value. After the calculation, you will find that it is still a positive, well, it is still equal to 0. The total sum of the net torque about the father is still equal to 0. So this would be a proof that it is in a static equilibrium. There are other situations which you would have a static equilibrium as well. And this is a slightly more complicated scenario. You have a beam and a worker is on the beam. So the beam is supported by 2 things. The first one is the string. These are cable actually at one end, and it is supported by the wall on the other end. So you have to be careful about the conditions of the wall. Now I will have to explain the last part of previous example later because I'm going through this one, going through the example 12.2. So here you have a wall that provides some support to the person, and there is a pin connection. This pin connection means that it allows the beam to be in equilibrium by providing forces at different directions. Typically, it would support the beam or any weight on it by a normal force that goes parallel to the beam. And at the same time, it would provide an upward support to the weight of the beam as well as the person on it. So in summary, you could add the two forces, this normal force and this, if you like, the support force, together by a reaction force R with an angle theta. So that is why you have the force R, at an angle theta, because we do not know what is the ratio between the normal force on the wall and the vertical support force by the pin. In any case, they add up together in a vector sum. So in order to find out the equilibrium, once again, we have the three equations. The force in the x direction must be in equilibrium. And then the force in the y direction has to be in equilibrium. Finally, the torque about any point would be, the net torque about any point would be equal to 0. Well, how will we be sure that a vertical force would be necessary? You could do the calculation, basically. And if that is not sufficient to provide the support, then you need the support. So at here, the idea is you have the tension in the cable. You have the tension in the cable. Sorry. You have the tension in the cable. Tension in the cable. You have the reaction force, and you have theta. Basically, three unknowns. And you have 1, 2, 3 equations. So in this way, you could solve the simultaneous equations by having by solving the 3 simultaneous equations. You could get the 3 unknowns. So that would be the whole idea. Of course, here you have a pin connection, and this pin connection would be providing various forces, not just in the horizontal sense, but in the vertical sense. Whether it is necessary or not, at the end you could calculate. If theta is equal to 0, that means no need for vertical force. So it is the most general case. And you calculate for the specific situation in your question. So this would be the calculation. Okay. Now, maybe I just go back to the question from one of your classmates. He was asking me to make a another a further explanation on this part. In the what if part. So as the equilibrium conditions require three things, it requires the sum of the forces in the x direction equal to 0, sum of the forces in the y direction equal to 0, sum of the torque about the set is equal to 0. Nothing, however, is told, nothing, however, is mentioned the location of the z-axis. It could be around the flocum, it could be around the father. So rather than considering the rotation about the flocum, here we consider the rotation about the father, and we try to calculate the net torque about the father's location. So that is the last part of the example 12.1. When you consider the net torque about the father's location, there are three forces that contribute to the torque. The first one is the weight of the board. Please check the question why it is the weight of the board. Second one is the weight of the daughter. The third one is the normal force that supports the whole system in the vertical direction. So distances are represented in the diagram already. So you will see the first one is the normal force contribution to torque. Second one, due to the weight of the board. And finally, the torque due to the daughter. The torque due to the daughter. And taking care of the positive and the negative senses carefully. And in this way, you would calculate the net torque about the father's location being 0. So that is the idea. And here we have another example for an extended object in equilibrium. This case, you have the ladder that is resting against a smooth wall. Now that often comes out in the question. That often come out in the question. That often come out in the question that you have conditions of the wall or conditions of surfaces that are mentioned. So here you have a smooth wall. A smooth wall, by definition, would have no frictional force. So if you just land the ladder on the wall, then what happens is it would not provide any frictional force. Any force could just be perpendicular to the surface. Any force could just be perpendicular to the surface. No frictional force. It is smooth once again. So what are the forces that act on this ladder? It is shown in the diagram below. You have the normal force from the ground. You have the ground that provides frictional force because it is resting on a surface, on the ground, with a coefficient of static friction being 0.4, so it has frictional force. And by common sense, you would fully expect the ladder to be sliding down like this. So it would be moving like this. Therefore, the frictional force would be in the opposite sense to stop the relative motion. Finally, you have the weight of the ladder that is acting at the center of the ladder. So this is the force diagram. finally, you have a wall, of course, that provides the normal force only. So what are the equations that we could set up? X direction, Y direction, and we could relate the let me see. We could also have the net torque about, in this case, the point O. The net torque is about the point O. So we are trying to find out the minimum angle theta minimum, in which the ladder, it is not slipping. If you have done that at home, I'm sure that it is not something very difficult to do. You try to put for example, the boom that you sweep the ground against the wall. If you put the boom at close to 90 degrees, it could rest quite well against the wall. But if you put the boom at 30 degrees, I'm sure that it would just come down. So there is a minimum value of theta in which the ladder or the boom can be supported. And when it hits the minimum angle, the frictional force should be at the maximum value. So here we set the P equals to the frictional force, the maximum static frictional force, which these two are the only horizontal forces. And the maximum static friction is equal to mu s times mg. Something I expect you to know by now because you are having the midterm next Monday. So in this way, you could once again calculate what is the value of theta minimum, because you are having three parameters. You have the N, you have the P, and you have the theta minimum in this case. So these are the techniques that we would use to solve the equilibrium problem. Now this one would be slightly more difficult because it involves the rotation about a certain point. So let's try to view it slowly as the last example. Here you have a person sitting on a wheelchair, and of course a wheelchair would have two wheels. So this is an important hint actually. You have the diagram that tells you the situation. The person is applying a force F, is applying a force F in a horizontal direction. And he is trying to go over the curb. So it is just one single step of the stairs. And the contact point is A. And the wheel is in contact with the ground surface at the point B. The person is trying to have the wheel rolling up over a sidewalk curb. So he is trying to basically lift the whole armchair and then go over the curb at the point A. So we are trying to determine what is the equilibrium breaking point. So it is the edge of the equilibrium, if you like. First, we try to draw the diagram. What are the forces acting on the wheel? The force diagram is at the bottom. You have the force from the person's arm, horizontal force F. And then you have the weight of the whole armchair and the person. And then finally, there is a reaction force R. We have no idea what is the direction of R because we are not sure whether there is a friction or not. But in any case, let us put it as R, and it acts at an angle theta from the horizontal. So we would solve the problem by considering equilibrium situation. First, we try to consider what is the force F necessary to cause the rotation. And as we are trying to take the advantage of the equilibrium calculation, we consider the net torque about the point A. Because if we take the torque about the point A, we could neglect altogether the contribution from R. R is acting at the point A, where the curb is in contact with the wheel. So we have the F times 2R minus H that generates a clockwise torque, and mg times D is this one, that generates the anti-clockwise torque. So they are in equilibrium at the breaking point. One thing you should notice is that here, mgd, when it comes to the equation, it becomes 700 Newton. Notice that the combined weight of the person and the wheelchair is actually 1,400 Newton. So why it becomes 700? Because your armchair has two wheels. So each wheel would take up 700 Newton. Altogether, it would be taking up 1,400 Newton. So that is why it becomes 700. And with that, the calculation would be quite straightforward. The force would become around 300 Newton. So you need to have the arm, each arm that holds the force of a 300 Newton to go over a curb. What is the size of a 300 Newton? It is basically 3 bags of rice. Each is 10 kilogram. So I'm sorry, I have to use an example that is easily understood by the Chinese because that is also my common experience. But yeah, it would be 30 liters of water as well if you are not familiar with what is the weight of a bag of rice. And once we got the value of F, we could calculate what is R and theta because we could consider equilibrium in the X and Y directions. Net force in the equilibrium must be equal to 0 in all directions, X direction and Y direction. So this would be just a simultaneous equation. So I would not say there is any particular difficulty for this one. Okay, now in your tutorial, you have 2 questions that are related to static equilibrium. And the calculations are not very difficult, I would say. Usually, you just need to write down all the force and the torque equations, and then you could solve the problems by solving simultaneous equation. Some of the possible tricks may be the presence of friction or the absence of a friction from the wall or the ground. If it is a smooth surface, it is only possible to provide the normal force. If it is a smooth surface, it is only possible to provide a normal force. There would not be any frictional force because it is a smooth surface. Or sometimes there will be strings, and then you would have to add in the contribution from the strings as well. So please take a look at the 2 tutorial questions. And if you have problems, you could always come to the consultation session or ask me after the class. Okay, I will stop the lesson at here, and we will continue on the Thursday. Thank you.